All right, number 3, find the equation of the tangent line to the graph of f of x is equal to x to the fourth plus 2x squared at the point where f prime of x is equal to 1. And so I'm going to use a lot of the calculator features. I'm actually not going to write very much down, just to showcase what the calculator can do for you. So let's go to y equals. Let's go ahead and plug in our x. So we have x to the fourth plus 2x squared. And I'm going to scroll over to the left to where my line is highlighted, and I actually can change the line shape. In this case, I'm making it bold. If you keep on going through, you'll see that it can be, this will be greater than, less than. You can look at it for a parametric equation. You can watch a ball cross by. You can have a dotted line, but then it goes back to your original. I'm just highlighting it, so my parent function is going to be a little bit bigger. And then next, I'm going to have the calculator graph my derivative. Now, what the calculator won't do for you is it won't tell you the derivative on the home screen. But what it will do is it'll graph the derivative for you. So we're going to go to Math and scroll down to Math 8 and derive. And we're going to plug in our parent function, that x to the fourth plus 2x squared. And then comma our independent variable x. And up to this point, you've been plugging in the instantaneous rate of change, a number at a point, the x value. Well, if the calculator wants, if we want the calculator to graph our derivative for us, I'm going to go ahead and plug in x, because I want the calculator to plug in all values of x, any number we can think of. And let's go ahead and graph it so you have an idea what it looks like. And so you can see that the bolded function that looks like a parabola is our quartic. And then the thinner line, which you can see, is our cubic. So if we take the derivative of quartic, which is to the fourth, if I decrease that by 1, the exponent by 1, I'm going to get a cubic. And so you can see our cubic coming in. Now I'm going to go ahead and go back to y equals, and so you can see the derivative a little bit better. I'm going to turn it off and hit graph. And the way that you turn off, you go over to your equal sign and not highlight it again. Whatever's highlighted is actually what's going to graph. And now we can actually just go ahead and see my cubic. What my problem is asking us to find is the equation of the tangent line given a certain slope value. In this case, if my cubic is a representation of all the different possible slopes at all these different types of x values, these are all these are graphing of m. This is m equals, maybe 2, m equals 1. So if I let me go to second table so see what I mean. Let me change my table. So table set. And I'm not going to have it ask me again. I'm just going to do second table. And then if you look at, or x equals 0, y2 is equal to 0. So at x equals 0, my slope is 0. At x equals 1, my slope is 8. At x equals 2, my slope of the tangent line will be 40. At x equals 3, the slope of my tangent line will be 120. If you scroll up to the negatives, you'll see the slope at x equals -1, the slope of my tangent line at that particular point will be -8. And so when you go to your graph, what these are is all the different possible m's. This is a graph of m's. So it'll be x comma, instead of x comma y, this will be x comma m. And these are all the different slopes. And so I want to know where m is equal to, where my dependent variable for my derivative is equal to 1. And so I'm going to use that by using the intersection. So I'm going to graph a horizontal line, y equals 1, hit graph. And I want to find the x coordinate. So I know what my m is. So I want to find what the x value at that point is on my derivative. So we can go to second trace, or calc, and go down to 5, which is the intersect. And then we're just going to go ahead and select both of my functions. And it gives us the x coordinate of 0.236. And so that's the x coordinate for the equation of my tangent line. But I also need to find my y coordinate. Now you have to be really careful. We want the y coordinate for the parent function, not the y coordinate for the derivative. The y coordinate of the derivative is the m of my tangent line. So I'm going to go to my home screen. And so I'm just going to memorize 0.236. And let's see here. Let's go to y. Let's turn this back on. And I'm going to plug in 0.236 into my equation. So I'm going to go to vars, y1, and plug in 0.236 into my equation. And this will get my y coordinates. Hit enter. And so my y coordinate for my tangent line is 0.114. So using the calculator, we know what m is. They gave it to us. M is 1. We found, using the derivative, we found what our x coordinate is. We found x was going to be 0.236. And then we plugged in 0.236 into f. And we got 0.114. And so the equation of my tangent line is y minus y1, which we found here, is equal to m, which they gave me earlier, times x minus x1, which we found by using the intersection. And that's probably one of the best ways to use your calculator. Number 4, using the table below, find the equation of the line tangent to h of x and g of x at x equals 8, provided h of x and g of x are differentiable functions. And so we're actually going to find two different tangent lines. And so my x-coordinate for both tangent lines is going to be the same. It's at 8. My y-coordinate for g of x is at 3, and his slope is found over here where you have that g prime of x. His slope is going to be 5. H of x is going to have a different slope. H of x's y-coordinate is at 9, and his slope, you see the h prime of x is over here, which is -4. So my tangent line equation for my g of x is going to be y minus 5, or excuse me, y plus 3 is equal to 5 times x minus 8. That's my g of x. My h of x tangent line equation is y minus 9 is equal to -4 x minus 8. And so these are, I showed you several different ways of finding tangent line. Please memorize the point slope formula. It will help you out tremendously.